Welcome to the tutorial about determining the role of other variables in a regression analysis. Here are the concepts that will be covered in this tutorial. The first concept is using regression to isolate the association between a primary predictor and the outcome. So say we want to know about the association between an exposure E and outcome O. We want to understand how an other variable may influence the exposure-outcome association. The other variable might play one of four possible roles. It might be a confounder, it might be an effect modifier, it might be an independent predictor, or not associated with the outcome. Here are short definitions for the four possible roles of the other variable. A confounder changes the relationship between the primary predictor, also called the primary exposure, abbreviated E, and the outcome, abbreviated O. An effect modifier modifies the effect of this exposure on the outcome. That means the association between the exposure and outcome is different in each category of the effect modifier variable. An independent predictor is significantly associated with the outcome even in the presence of the primary exposure. And if a variable is not associated, it means it is not a significant predictor of the outcome in an adjusted model. There are 5 basic steps to determine the role of the other variable. We will be going through these steps one by one in this tutorial. The first step is to conduct a crude analysis, which means building and running a crude model in SAS. A crude model is a regression model, linear or logistic, that contains only the primary predictor, and the purpose is to look at the primary predictor and outcome association without adjusting for any other variables. Here's what a linear crude regression model would look like in SAS if we had a scale level outcome. Notice there's just the one exposure. Here is what a logistic crude regression model would look like if we had a binary outcome. And note that we have this optional class statement. The purpose of this statement is to set a reference category if we had any exposure variables that had over 2 categories. The next step is to determine whether the other variable could, in theory, be a confounder, and we would do that by going through those 3 criteria we've talked about in class. The next step in determining the role of the other variable is to stratify by the other variable and conduct a stratified analysis. So let's talk a little bit about stratification. What is stratification? Well, stratification is the act of sorting data into distinct categories. Categorical variables have predetermined categories, which we call strata, but scale variables must be collapsed into categories. So if the other variable is categorical, we don't need to worry about creating categories. Categorical variables have already been stratified. For example, the variable educational attainment is a categorical variable with 4 categories or 4 strata. If we had a scale variable, we would have to use SAS to collapse it into categories or strata. So for example, if we had age in years, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., we could collapse it into, say, 5 different categories. A stratified analysis means that we calculate the exposure-outcome association separately for each strata. For example, if there were a study of coffee intake and bladder cancer stratified by smoking status, which would be the other variable, we would calculate that association between coffee intake, the exposure, and bladder cancer, the outcome, separately for smokers versus non-smokers. In SAS, the stratification process looks like this. So the first step in stratification is to sort by the other variable, and that is the proc sort command. The next step in SAS is to run a stratified regression model. Here's what it would look like if your model were linear, that is, if you have a scale outcome. The only difference between this and what you've done before is that you insert a by statement right here. So you're going to run this model by this other variable. In other words, 4 categories of this other variable. And the same thing down here in the logistic regression example. After we run the stratified model in SAS, we need to interpret the output. The output is going to be the association between that primary exposure and outcome for each category of the other variable. If the stratum-specific associations are the same as each other, but different than the crude, then the other variable is a confounder. However, if the stratum-specific associations are different from each other and different from the crude, then the other variable is an effect modifier. The theoretical explanation of how stratification works to elucidate confounding is that it removes the effect of the other variable because everyone in the same stratum has the same value of the other variable, because everyone in the stratum is smokers and everyone in the stratum is non-smokers. So you can see, because there was a change in the estimates, that the crude association was confounded by smoking status. After stratifying, we still do see an association between coffee intake and bladder cancer, but it isn't confounded by smoking status now. The theoretical explanation of how stratification works to elucidate an effect modifier is that it shows us that the association for that exposure and outcome is different for the different categories of this other variable, the effect modifier. So again, here's the crude model containing everybody. When we stratify by smoking status, we have a separate coffee bladder cancer association for smokers and non-smokers, and the association is different in each category, and it is also different than the crude. So that means smoking modifies the effect of coffee intake on bladder cancer. So that was stratification. The next step, if the variable is not a confounder or an effect modifier, is to run an adjusted analysis. So adjusting. Adjusting or controlling refers to a process in a regression model where secondary predictors are held constant. The association between the primary predictor and outcome can be interpreted then as the association when the other predictors in the model are held at their mean value, if the other predictors are scale, or reference category, if the predictors are categorical. Here's what an adjusted analysis looks like in SAS. And this should look pretty familiar because we've already been conducting adjusted analyses. You'll see the only difference from the crude model is that in addition to our primary predictor, also called our exposure, we have some secondary predictors. So now let's go to SAS. And walk through how to determine the role of the other variable. For this analysis, we'll be using the dataset called child injury and the SAS code called var_role_tutorial. These are both in the tutorials folder in SAS, so please copy them to your class.stat folder and then double click this one to open it up. And you can also follow along with the coding of the variables in the injury death codebook, which is available in Canvas in the other resources module. Our research question in this tutorial is, what role does annual household income play in the relationship between mother's age when the child was born and the child dying from injury between ages 0 and 4? Exposure is age_moms, that's age measured in years. The outcome is death from injury, 0 no, 1 yes. The other variable is income in 5 categories. So let's go to SAS and run our libname statement, and then let's run descriptive statistics for the variables in the research question. We'll use a proc_freq command for our categorical variables, and we'll use a proc_univariate command for our scale level variable. Here's just a summary of our findings. So the first step in determining the role of this other variable, which is annual household income, is to conduct a crude analysis. So here we'll set up the regression model as a logistic regression model because the outcome is binary. Death has 2 categories. The primary exposure is the mother's age in years, so we don't need to include a class statement because this is not a categorical variable. We would like to include the DESC statement at the end of the first line because we want SAS to model the odds of death yes, instead of the odds of death no, which would be its default if we didn't add the descending statement. Here is a summary of our output. We can see that the overall model is significant. We can interpret the adjusted R². We can see that the primary exposure, mom's age, is a significant predictor of the outcome, and we can then interpret the odds ratio estimate. Now we should determine whether the other variable, annual household income, could in theory be a confounder. We do this by going through the 3 criteria. First, is annual household income associated with the exposure? Well, those in midlife who are usually older usually make more money, so yes. 2, is the potential confounder an independent risk factor for the outcome? We don't know, but theoretically that could be possible, so we'll say that criteria is met. Number 3, mother's age shouldn't lead to annual household income, but it actually might, so this criteria might not be met. But we will continue with the analysis and see what happens. Now we should stratify by annual household income and conduct a stratified analysis. In SAS, the first thing we want to do is sort the data by the other variable, so we use this proc_sort command. Next, we want to stratify our logistic regression model by the other variable. SAS will provide the results for each category of income. So essentially it just runs a separate regression model for each income category. So we should check the overall significance of each model and the significance of that primary exposure in each model. And when we scroll through the output, we can see that each category of income has a significant overall model, and in each of these models, the primary predictor, mother's age, is significant. Now we should compare the stratum-specific associations and the crude association to see if the variable is a confounder or an effect modifier. Here are the results from all 5 of the models showing the association between mom's age and injury death for each category of income. And we can see here a lowest value and a highest value. These don't look too different. Let's put them in a table format so we can look at them all together and compare them with the crude. When we compare those stratum-specific estimates, we first want to know if they are the same as each other but different than the crude. So are they the same as each other? Well, let's use the 10% rule. So for the associations to be within 10% of each other, that means the maximum value must be more than 10% higher than the minimum value. We can actually use an online percentage calculator to help us if we wanted to. And you can find the link right there. So let's use the percentage calculator to compare the stratum-specific associations and apply the 10% rule. So we want to know if our max value, 0.933, is at least 10% higher than the minimum value, 0.870. So we plug in the numbers to our percentage calculator. We want to know 10% of 0.870, which is 0.087. We're going to add this 0.087 to our minimum value, it's the 10% of it, and we end up with 0.957, which is higher than 0.933. So we can say our max value of 0.933 is not 10% higher than the minimum value, and we can conclude that the stratum-specific associations are not 10% different. So we found that the stratum-specific associations aren't significantly different from each other, but now we want to know if they are different from the crude association. To compare the stratum-specific and crude associations, we can again apply the 10% rule. The way we do this is by first computing the average stratum-specific association. So we add them all up, divide by the number of categories, and we get 0.9046. Then we look at our odds ratio from our crude model, and we want to know if this average stratum-specific association is at least 10% higher than this value from the crude model. So we take that minimum value, we add 10% of that minimum value to get 0.9768, and that is the number that is 10% higher than the minimum value. But our stratum-specific average is not that high, so we can conclude that the stratum-specific associations are not 10% different than the crude. In our 10% analyses, we found that the stratum-specific associations are not 10% different from each other, and they're not 10% different than the crude. This means income is not a confounder, and income is not an effect modifier. If we had found one of these things to be true, we would stop our analysis and report our results accordingly. But in this case, since the other variable is not a confounder or effect modifier, we need to conduct an adjusted analysis. And this will tell us whether the other variable is significantly associated with the outcome, which means it would be an independent predictor. Our adjusted analysis looks like this. We're going to include a class command because income is a categorical variable with more than 2 categories. We're going to specify that the reference category for income is 5, so that's the highest value, so we want to compare all the lower values to the highest value. And you can see we have our primary exposure just like in the crude model, but now we have added the other variable income. Here are the results of our adjusted analysis. The overall model is significant. We can interpret the adjusted R squared. We can look at the significant predictors, which are highlighted here. We can see that the mom's age variable is still significantly associated in the presence of the income variable. And we can also see that 2 categories of income are significantly associated with the outcome, injury death. So in our 4th step, if the other variable, any category of that other variable, is significantly associated with the outcome, we can call it an independent predictor. So we see that the two lowest income categories compared to the highest are significantly associated with the outcome. So we can say income is an independent predictor. If none of the categories of income, that other variable, had been associated with the outcome in the adjusted model, then we would say the other variable, income, was not associated and end our analysis at that and report accordingly. So now that you've identified the role of that other variable, let's talk about how you should report the results. If the other variable is a confounder, report the adjusted association. And note you'll need to conduct an adjusted analysis like we did in step 4. When we're talking about associations in this table, we're talking about the association between the exposure and the outcome, which will be a beta coefficient if the regression model was linear, or an odds ratio if the regression model was logistic. So moving on, if the variable was an effect modifier, you'll report all of these significant stratum-specific associations. If the variable was an independent predictor, you'll report the adjusted association for both variables, so for both the primary exposure and the other variable. If you found that the other variable was not associated, you can just report the crude association. Here's a table that shows the results from all the models we ran. So here's the crude model, and all of these odds ratios are the odds of death due to injury, which is the outcome, associated with mother's age, our primary exposure. Here you can see in the adjusted model, we've also added income. We've adjusted the association between mother's age and injury death by income. You could also interpret these numbers as the association between annual income and odds of death due to injury adjusted for mother's age. Finally, here are the results from the stratified model, where in each of these categories, we have the association between the exposure, mother's age, and outcome, death due to injury. So if the other variable is a confounder, what you'll report is the adjusted model. So you'll just report what's in this rectangle here. And then you'll interpret the odds ratio for that primary predictor in a sentence. For example, here's just that adjusted model, and here's an interpretation of that odds ratio. If you found that the other variable is an effect modifier, you'll just report the stratum-specific association, so just what's within this rectangle. And you'll interpret the ORs for all the significant stratum-specific associations. So for example, here is just the table for the stratified model, and I've started interpreting for all 5 categories which are significant. Next, if you found out that the other variable is an independent predictor, you would report the adjusted model, just like you would if the variable were a confounder. However, the difference here is that you would interpret the ORs for all the significant predictors, whereas if the variable were a confounder, you would report only the adjusted association between the primary predictor and outcome. So here's our example of what we would do if we found that the other variable is an independent predictor. We would write a sentence interpreting each one of the significant odds ratios. And finally, if the other variable is not associated, we would just have to make a table of the crude model and interpret that odds ratio in a sentence, which is exemplified here. So in summary, we can use logistic regression models to learn about an association between a single exposure and an outcome, considering the role that other variables may play. Possible roles for other variables include confounder, effect modifier, independent predictor, or not associated. To figure out what role another variable plays, we can conduct a crude and stratified analysis and compare the results to determine if the other variable is a confounder or effect modifier. If it is not either of those, we can conduct an adjusted analysis to determine if the other variable is an independent predictor or not associated. And finally, how we report the results depends on the role of the other variable, as you saw in the previous tables. And that concludes this tutorial on identifying the role of the other variable.